Hello, I'm Shimon and I want to present to you my paper. Two models are proposed. One is based on deep learning, trying to reach high cognitive functions, and the second is mainly based on psychology and sociology. We start with the deep learning model. Inspired by Jeff Hawkins' predict structure of the human neocortex, we turned it into discriminative generative structure, or the encoder-decoder structure. Or in more details, we encode all possible information coming from text and vision, finally into some extracted features that represents the whole situation. And upsample it to the actuators for a proper response. Now we'll see different components and their possible implementations that exist in literature. The first part is extracting features separately from sensors and text. This part is inspired by image captioning test. Then we extract these joint features further into longer timescale tasks by using intermediate tasks. These tasks are intended to recognize relationships between perceived objects. Some papers focus on pairwise interactions, while others focus on higher order interactions. These relationships or actions are spread over different timescales. These hierarchical temporal RNNs can be implemented via different clock rates or via sliding or shifted LSTM blocks or via dilated causal convolution. We see that the decoder is also hierarchically temporally constructed as a minor image of the perceptual encoder with skip connections, which can be, for example, copy or normalization, addition, and more. Now we describe briefly the training phases. First, it learns to fuse multi-modal inputs to establish basic semantic concepts. Then it starts by learning basic elements, objects, and then continue with composite objects and relations. After this proper symbolic comprehension, it turns to learn how to respond correctly within the common supervised learning approach. Just as in the encoder training, here it performed also gradually, from short to long-term tasks. Now we go over some details regarding phases 2 and 3. Inspired by these implementations, we propose to do similarly here. In the upper left corner is a snapshot of our system, and in the middle is its equivalence in image captioning system. The right top describes the inner structure of the RNN in a folded and unfolded forms. Step 2 is actually sending the hidden state of the first layer of RNN to some decoder for some supervised task, referred here as intermediate task, in order to learn the embedding in matrices U and V. Step 3, using these embeddings to produce outputs for the next layer of the RNN. Now back to the third phase. We illustrate how gradual learning is done. Each time we proceed to higher level, the lower levels are freezed, while the more higher level do not participate in training. Now we can view this idea better in 3 dimensions. Here we see fast tasks, meaning fast input with fast reactions. Slow tasks allow a slower processing of the incoming information, while gaining control over the fast tasks by constraining their action. When higher tasks are operating, they decide upon the more restrictive actions available for the lower tasks executions. We also have skip connections for the lower level to allow it to continue operating almost independently. Specifically, the connection that fast tasks had in previous slide. Next layers operate in the same fashion. This resembles the biology-based approach where after repeating some task, it becomes automatic for us such that our mind is free from concentrating upon it and now can deal with other tasks while performing these low-level tasks. This potentially can introduce also working memory or thinking in higher available layers to solve difficult tasks. How is it possible? Because the inputs are very slow or stable. So these layers don't need to process the fast tasks. So they left to deal with the harder tasks provided in the text input. The round plate represents these possible cognitive functions. Now we represent our second model, the Associative Knowledge Representation Model, or in short, AKREM. It deals with several types of memories, short, long, and working one. And it is based mainly on our communication model, as will be described now. We start with the assumption that our inner models of the world are totally different. We argue that each of us is like a black box with respect to the others, and it is expressed via low quality of communication, resulting with misunderstandings. Black box principle isn't appropriate only for human intelligence, but also for AI. Assuming that AI's internal perception cannot be directly interpreted by us, it must undergo over some means of communication. All this section about communication with the AI emphasizes my opinion about black box issue people have with deep learning. My thought is that logic and interpretability is the outcome of neural networks. Hence, neural networks probably were designed by nature to be unexplainable, since explainability is an expression of intelligence, but not its vessel. Therefore, we can reason and understand AI only through communication with it, not via analyzing its internal structure. The basic assumption here is that communication must be logical and consistent, along with other communicative characteristics. We can imagine ourselves what mental image a person has before he turns it into words and passing it to some recipient. Here's some examples for that. A description of composing Lego elements, a description of a dog doing something, or a simple description of an elephant. It can be any type of message, such as story, how to do something, and more. Anyway, despite the agreeable communication between us, the interpretability of each of us is different and subjective. It is due to different perception or world models each of us has, models of ourselves and also of others. Hence, sometimes the difference between the original message to the perceived one can be in the range from small to huge, where misunderstanding starts to occur. And even worse, none of the participants are aware of this happening. We can even extend the number of models we have for even ourselves, such as different ways we behave and express ourselves with different people or within different surroundings, and so on. Since all of us are in different state of mind all the time, we must eliminate this gap by starting our message in the most general form and gradually lead the listener to our specific and accurate message. Hence, we start the message generally and end it with specificity. Similarly, this presentation must be constructed consistently for the audience to understand it. For better communication, especially for the common sense or the lots of unspoken information, both the recipients and the sender must have models of themselves and others. Expanding the modeling for communication we have seen previously, we can infer that we actually modeling everything, each thing depending on our interaction with it, which could also be passive, such as by observing or mimicking, or active. It applies to ourselves, to different people with different interactions, and to different groups of people. Similarly, it applies to each object or group of objects, and similarly, it applies to animals. Now we go into some details. Based on some of the communication principles we have seen so far, we can derive AKREM, expressing how information is represented in the memory, and to serve as a basis for cognition. We demonstrate how associative memory is generated in a hierarchical form from a sequence of phrases or sentences. Here we start from some phrase, next one, and the next one, and the next one, and then suddenly it's a different kind of event. So we can ask ourselves, what is common to this previous group? and we summarize it. Now we continue in the same fashion. Again, a new event, but we will continue in a less detailed form. Now we go over to retrieval. This representation is also comfortable to examine comprehension. For example, asking questions about the message that we received or a story as we've seen just now. Here, for example, a question. And now we'll see how we move along this hierarchy. You first search in the highest levels, then in the relevant episode you search in its lower levels, till you find what you need. Please note that we look mostly in the lower levels because the descriptions written in the higher ones are misleading. It is not representing a sentence, but the essence of facts in the lower levels. It is actually a speechless representation of a grouping of the lower levels. Here's another example. As you can see, the trajectories can be back and forth in any order. Now we can view it more generally. In order to both generate hierarchy from a sequence or vice versa, some kind of order has to be stored. For example, chronological or causal one. And it has to be in all the levels of the plot. See, for example, the temporal trail in the top view figure. The lowest level contains most common used triggered concepts or events, which are associated to a huge amount of hierarchies. The higher you go in a given hierarchy, the more specific the message becomes, and it is more differentiated from other hierarchies. Here's a side view of this hierarchy. We can see in the top written working memory, but another model can be where the whole hierarchy is inside the working memory. And the top is simply the hierarchy's essence. The trigger terms that construct the lowest levels of any hierarchy can be, for example, triggered neurons in the DLM presented earlier. Or it could be the perceived embeddings in the highest temporal levels in the DLM. Now we talk a bit about the memory organization or structure. We can assume that simple sensory perception is using base memory similar to system 0, automatic system, no thinking system. Then it provokes long-term memory concepts or events, uploading it to the working memory. And at sleeping period, the system somehow decides what to consolidate into long-term memory and what not, due to unimportance or similar memories already exist. Note that the long-term memory and the working memory are not connected to the sensors and the executions. Perhaps, since this is the abstract thinking, where thinking, depending on some task or some external instruction, is moving in a purposeful trajectories, mostly or sometimes regardless to the inputs. Actually, we assume that there's a permanent associative wandering in long-term memory, which produces some final or intermediate results which are updated in working memory. All this wandering must have some purpose, as mentioned earlier. So there's some external will inserted in this process, guiding it. My belief is that we solve any situation or problem this way, by simply jumping associatively from hierarchy to hierarchy, or within hierarchy, along with some guiding will, which is about searching for something, gathering some intermediate insights to eventually resolve with some response, which could be, for example, a good solution or bad solution or no solution at all. Actually, we can regard the base memory simple as part of the long-term memory, to be as the most frequent used in long-term memory, almost automatic. Thank you for listening.